Okay, good. So during the last lecture we finished the Just C part, and today we'll start with the nice C++ features. So let's create a new project. C++ basics. Okay, and the most noteworthy ability in C++ over C is that C++ is a object-oriented language, so you can create complex objects. So in plain C, what we could do is we could simply have functions and structures, basically just data in memory on which we could operate, but the things were not like integrated into each other in any particularly meaningful way. C++ extends this in a very important way, such that we can have objects, and the objects can have their own functions which act on these objects. On the hardware side, this in principle is not different than just having a function that takes a struct as a first argument and does something with it. But from the perspective of the code developer, it is extremely more convenient than working with just single functions and structures. So let's start by creating such a complex object. So in C++, we call them classes. Although if we have a CPP file, we could also use the struct keyword to create an object. It would be almost identical in behavior. So kind of the structs from the old C have been extended. In a C file, you however cannot use any classes or any advanced features that you can use in C++. So let's call it C my class. It's customary to start class names with a C, indicating that it is a class. But of course this is purely optional, so you could name it however you want. Then, like with a struct, we have the opening and closing curly brackets and a semicolon at the end. And like with structs, it can have member variables. So let's say int my int. But there is already one important difference. If we now define an object of type my class and we type dot, we see that it actually doesn't offer us any members. So in C, everything we had was accessible always, which means that you could in principle also access some internal protected, in quotations, protected variables, which would not be supposed, for example, to be modified just by the user of some library, which would be only supposed to be modified by some internal functions. But since everything was just a memory block where you can read and write it everywhere, then there was not even semantically a way to distinguish things. In C++, where you have classes, what you can do is you can define members, whether they are public, private, or protected, and this will define the scope in which those variables are accessible. Of course, it still is just a memory block, so if you know the address of a variable, even if the language doesn't allow you to access, you could still write to it, just in a hacky way, which we might try later, just for fun. But obviously, when you're writing programs, then you are not trying to break them on purpose. So instead, you will be using the mechanism and syntax that the language gives you, and thus accessing certain variables will only be allowed from certain scopes, which helps keeping the code structured and avoids issues where you would get, for example, into an inconsistent state if you would only change one variable. Instead, what you would have, for example, would be a function that is supposed to do a change to your object, and this function can then be implemented in a way that will update multiple variables and ensure that it does this in a correct way. So to change the scope in which a variable is generally a member of a class is visible, we use a keyword like public or private or protected, and basically everything after this keyword is in this scope until the next access keyword is specified. And the default access modifier for a class is private, so unless you define something as something else, if you write things just at the beginning here as we did before, then it will be private, but it's equivalent to being here, so it's not a very large change. And if we would define our class using the struct keyword, then the default modifier would be public, and this is on the C++ level pretty much the only difference between using class and struct. But obviously it is customary to always use class whenever it makes sense. But it's simply good to know that if you have a struct and you would want to, for some reason, add just a function to the struct or do something with it slightly more advanced, you can do with it everything that you can do with a class anyways. So now that we have defined this as public, we can access it. We should be able, sorry, it's I put it into private again. Public. And now we can access it and, for example, assign to it a value. So at this point it's obviously not that much different. The important things are the functions that we can define. And just about the scope, so public means that anything that has a has an object of this type can access it. Private would usually mean only the class and potentially directly derived classes, while protected is a special case, because when you have something as protected, you can define with the friend keyword other classes which would be allowed to access your protected members. So you can have, for example, two classes which in some way have to cooperate, and you want them to be able to access their internal members, but you don't want the general user of those classes to be able to access those members. So this is a use case where you would use this protected mechanism. In principle, you can also define a single function as a friend, so it is quite flexible actually. Okay, so let's start with the next thing. Let's define a function. Void my, or let's call it set my int. Let's put my int again to be protected. We don't care for private. Let's put it at the top and at the comment that it's the default. Okay, so we have our protected variable and we have our function set my int value. It will have some value that it sets, and usually when defining classes it is customary to create a header file. So here for simplicity, at the beginning we will not be doing this. We will be just writing the classes at the beginning of our file. But usually you would put the classes in header files, and what you would then do is you would put the functions which you want to define as a body somewhere in one of your CPP files like this. But what you also can do alternatively is you can just write the function directly inside of your header. This is usually frowned upon unless they are very short functions. So if you have something like just set a variable, get a variable, then it's fine to do it in the header. But if you would have like something complicated that does like half a page of code or even just a few tens of lines, then you would usually try to put it in a C++ file. The reason for that is twofold. For once, the more stuff you have in your headers, the slower your entire project will build, because with every include, the stuff needs to be reprocessed at least to some extent. So this is not great. The other reason is that usually you want the headers to be like a sort of functional documentation. So basically, if you don't write documentation, you just tell people, okay, just read the header, look the comments up there, and that's it. So that might not be great, but if you only have the functions and they are sorted in a reasonable way, maybe with a few comments and with argument names which are intelligible and descriptive, then you can already learn a lot of what a class is doing just from reading the headers. And of course, if you would have the single functions interrupted by large code blocks that do some internal stuff, that would of course interrupt the the reading, so it would not be so great. But as said, since we will be doing simple things, to keep everything in one place for today, we will just write most of the things in the headers. So here, let's just assign the value. In principle, we can make it a one-line function, and of course what we would want would be a way to get the function as well, get the value as well, I mean. And what we can do with functions is we can then define them normally, or we can add the const modifier. The const modifier pretty much defines us the type as what the variables which we have here will be treated. So normal variables which are non-const, if you are inside the const function, will be seen as if they would be const. There is a way to bypass this, because there are scenarios where you might want to have a const function and most of the variables be const, but one of the variables you want to be mutable, and you can do it with the mutable keyword. So if you define a variable as then it will be mutable even inside the const function. But for our use case here, we don't need that, so we'll leave it as is. And here, let's just quickly set a value 1, and then get the value. Let's print it maybe. So let's include something. Hash include as the value. And let's print f that. F. And usually when referring to function names, you would refer, like if you just are referring in documentation, unless it's explicitly clear from the context, you would write the class name double point function name, as you do when you want to define a function in the body, because this really tells you where the function would belong to. And if you would look on a export table of a DLL that exports a class, you would see that the names of the exported functions are also decorated in a similar way. And of course it's a get, not a set. %d. So as simple as it gets for now. And some return 0. We can run it. It will of course just print 1 to the console. So as simple as it gets. And what we can do is we can take a look how this is implemented on the hardware level. So we put a breakpoint, and then we look what code the compiler generated for us. Although before we do that, we should, like with our previous examples, disable a few features that complicates things. So we don't want we don't want this. Code generation, runtime checks, we don't want this, and linker, and we don't want that either. Okay, that should give us a cleaned up simple code. So okay, so we see we have here set. Okay, so that's fine. So we put so we put the argument into the EDX register, and we remember previously in in normal C, when we had a function which takes one argument, the first argument would go into the RCX register and not the D register. Here it's different. The first argument goes into the second register, and what goes into the first register as the first argument is a pointer to the object itself. So the address of this thing is passed always as a first argument to the function, because when you think about on a hardware level, a function is not really related to any object in memory in any physical way. So the whole association that is created by the C++ language is pretty much purely artificial. We will also take a look in one of the later lectures on we will basically just have a C++ class with its functions and all the nice things it can do. It will write a normal C file, so with no C++ function, no compiler support for C++. And then we will still be able to operate the objects generated by the C++ portion by handcrafting functions which explicitly know the structure, which take the pointer to the object as a first argument, and so on. So we will see that pretty much everything, if not most, or maybe the other way around, most if not everything, in C++ that you can do, you could also in principle do with C. it would be just much more cumbersome, especially when we later go to things like templates. These are super convenient to avoid a redundant or rather repetitive code. And of course, there is no mechanism for that in C. So you would just need to implement 100 functions for 100 different data types by hand. While here, using templates, the compiler can do this for you based on a template function. But that's something for the future. So, as said, this is how this more or less behaves when we step into it and just end up in our function. So everything is quite simple. The function doesn't do much, it just sets a value and then returns. So we don't need to inspect this. What we can of course take a look is what we would see if we don't initialize the value. Okay, here in this case it gave us 0, but of course depending on the presets of our compiler, we might also have gotten a CC value indicating non-initialized memory and things like that. So if we re-enable the runtime checks, for example, let's see, code generation, and then we will run it, then we see that we get some garbage value, which on purpose was initialized this way such that we notice that we are using some garbage value. And there are a couple ways how we can fix this. I mean, the obvious wrong way would be just to call a set on every variable, but this would not be something you want. So what we would want is then a modern way to do this is you can specify an initial value when defining this variable. This will make when the class is constructed, the initial value is automatically set for you, which is quite convenient. As you see here, it just keeps the value whatever we tell it to. And of course we can later change it if we call set. So this really is just the initial value. But another much more powerful mechanism which can be used is to create a so-called constructor function. So one thing that I guess should be intuitive at this point is that if we have here a value, whatever it might be, that there needs to be code which will execute this. So when we create the object here, in this case we can actually oops, that was the wrong button, put a breakpoint and see how this case would look. And we see here that there is a function which has been created for us, which we don't see here at all. And if we step into it, we end up in a constructor which the compiler made for us, which will for which we don't have a source code here, but what it will do effectively, it will just do this initialization. And of course, if we would have more variables, it would do more of these initializations. But this actually a rather well, new is maybe relative, because C++ by now has been updated many times, and this is maybe a feature from C11 or so over 10 years old. So I cannot say it's really new, but like when you would have the very old C98, for example, then you would not be able to initialize things directly in the header like this. You would really every time need to create the constructor function, which simply is defined as a function without a return value, with the same name as the class itself. And then what you would do, of course, would be you would put all your initializations inside your constructor, however many you have, which is also quite useful, because in principle you can also, for example, initialize something with a defined random value. So you could call a function here that gives you a random value. We could do that, for example. Zack. So we always initialize it to a random value, but we know that this value will be random. It will not be garbage from memory. It will be something mildly random, at least. So the run function is not cryptographically random in that sense. It's it needs to be initialized with srand, where you can pass some value. Usually you would, for example, take the timer. But if you initialize srand with, let's say, if you initialize it with a constant value, let's say 1, and then you call rand, you will get the exact same, in quotation, random value out. And then you call rand again, you will get another value which will look random, but will be again the same. Basically, the rand function will go through the same sequence, because it always starts with the same initialization, and then it just processes the data in a circle. And in principle, unless you are using hardware as hardware features for generating truly random numbers from the physics of the CPU or another component made for it. Unless you do this, you will never get a random number out of a software system. There are, of course, various grades of random number generators. So in the sense that RAND is a particularly simple and trivial one, but there are ones which have much more internal processing and will create numbers where it is much more difficult to predict what would be the next value unless you know with what it was initialized, basically. But if you know that the initialization vector, you can replicate everything. So just this to be said about this as a small detour about how rand functions. But as said, it is quite nice that you can in the constructor initialize. And of course, you could have I mean, it's like a normal function. You can do anything. You can allocate memory there. You can create complex other objects. You can do whatever you want. And then each time when you instantiate your class, this constructor will be called. So in this case, we have created our own one. And now if we step through it, then we end up here. We see the source code in our own constructor. We don't have much here. We just have the call to the rand function. For which it needed to load the symbols, but we don't care about it. And then of course we jump out. And what you of course also can have is a sort of let's say hybrid approach. Let's call this one. Let's make it like this. So we define one to be 0, and then we want to generate the other one to be random. And when we what will now happen is that you will have a constructor calling another constructor, which is, so we start again here. We call our default constructor zack zack, which then implements at some point the mechanism to set the value to 0. Let's see, locals. It's already made it 0. Let's then start again. So we have here my class. So you see, it's not initialized with anything. Now we are starting to step into. This is not yet fully initialized. Okay. So we are starting, and as you see, it kind of moved some code here before. So instead of creating a second function, it just adds some code to the beginning of our function before we can do anything, which performs the initialization of the things which we have initialized this way. And then we arrive at our own code here. And then, well, we can actually go out of that. And once we are out, then we return to our calling function. And what you of course can also have is you can have different constructors which do different things, and depending on which arguments you pass to them, they will perform different operations. So we can, for example, if we have no arguments, then we'll call the top constructor, but if we add the argument, then we'll call the lower constructor and then do this assignment. And in principle, we could from this constructor also call the other one if we would want to, but there is no need to do this right now. We can just quickly run it just to see that we will end up in another one. Zack, zack, zack. Here it again initializes stuff, and then it goes back inside our own code, which then sets the rand value as we wanted. And there is another function which is comparably important. It's called the destructor. It's basically just a tilde prefixed name of the class, and there can only be one, like the Highlander. You cannot have two destructors. And the purpose of this function is that whenever this class gets destroyed, then this will be called, and you can perform internal cleanup. So let's construct a more sophisticated example. So let's say we have asterisk rands is equals null ptr. So we have multiple random numbers, and then we malloc size of int well one is enough, but let's say we want to have 3 of them. And asterisk. Okay, and then we will send orange. Actually, we can use a loop for. Actually, we should do it with differently. Int count, like 3. So what you always should try to avoid is hard-coded numbers that do something, because then if you would change one of them and forget to change the other one, you will run into some sort of problem. So we could of course have here less than 3 and 3 times something, but then if we change only one of them, then we will do bad things. So whenever you are doing such things, just make another variable, assign the value to it. You could in principle of course use a preprocessor definition instead. You could actually define this as const. That will allow the compiler to do some more optimizations, but generally the whole idea is that you will, whenever possible, try to avoid using the same number in multiple places. How you avoid that is up to you. Okay, and here, since we have only one entry, then we just do it like this. So we have different size of the arrays, and then we of course need to free it. And this we do in the destructor. In principle, we could also have like an if this is, then free it. But since you can call free on null, then you don't need to do this check. So free is defined such that it will work on null. But what we, for example, should have done is to check whether this thing gave us a valid address or gave us null, because this can happen. It could give us null if there is no memory free in the system, and then the rest of the operations would of course be invalid. But the problem is that inside a constructor you cannot kind of return a error value. You can only throw an exception, but this will be something for later. So C++ exceptions add another level of complexity to the simple exceptions which we have already seen. But what we at least can do is we can just avoid using it if it's not okay, and then we could, for example, have a function for is valid. Oops. Const return gleich 0 ptr, something like this, so that we create our class and then we check is it valid, i.e. was it created successfully. There might be many different conditions. For example, you could have a class which represents a serial port, like you use to communicate to an Arduino, or a huge amount of scientific equipment also uses RS-232, i.e. a serial communication interface to talk to. And you could have a class where you initialize the COM port number and the baud rate and something, and then the constructor would try to open the port, and it might already fail to open the port if the specified port number doesn't exist on the system. And then of course it would not do any of the other operations, and then once you created your class, you would check with a isValid function whether actually it was able to initialize itself correctly. So this is not just something useful in case of low memory situations, which on modern systems people tend to assume this will never happen and don't care. And if it happens, then things start crashing. So you should, when possible, always try to make your code fail safe, even for situations where you assume that they are very unlikely. If they are not impossible, they could happen, and this means they should be handled correctly. But as said, there are many situations where it might be a normal process of your application's operation to fail in some way. For example, when you unplug a RS-232 USB adapter, then the COM port goes away, then the class, which before could be initialized fine, now will have to be able to return some sort of error. Another approach, of course, would also be to create a function which would have the purpose of initialization. So we would first create something just with maybe an empty constructor, and then you would call an initialization function, which then would be able to return you a value. Or as said, from the constructor you can also throw exceptions, which we will take a look on a bit later. Right, so let's now take a look on our destructor. So the way this works is when a class is defined, as said, it constructs, and when it goes out of scope or is deleted, it will automatically then call the destructor. So going out of scope in this case means if you have a object defined on the stack, then if the curly brackets belonging to this code block close, then the thing goes out of scope and then it needs to be destroyed. So we'll put a breakpoint here, run it, and we will see that here it calls the destructor functions simply because we close the brackets. And then once we are in our destructor, we can then free our memory and everything works nicely. Now the other scenario, of course, is if you allocate things on the heap. So let's do it maybe here. Or let's actually, we couldn't do it somewhere else. So let's do it here. We'll call it P to indicate that it is a pointer. We do not specify anything, but we need to make a new one. So we use the new. That's the first new. Well, not the first new thing. One of the new things that you will learn today. In C, you always use malloc or something that does its function. You could use a virtual alloc from the Windows API, but that would be a very Windows specific. In C++, when you are creating an object, you are using the new keyword. And then you, of course, after then you specify what it should be. So in this case, the class name. And you can specify the constructor. So in this case, we can specify nothing to invoke the uppercase. But you could provide here arguments. And what this new operator does is it will allocate memory for us. And then on the allocated memory, it will call this constructor. And the way this is implemented, the new operator is part of the C++ runtime. So we actually have source code for what this new thing does, and we could override this new operator with some own one. So there are use cases where you might want to have some own memory management and not be forced to use the application's default memory management. And in such scenarios, it is very useful to be able to override the new operator, which then will allow you to use some own memory. And this can be done in a couple of ways, but for now let's just stick to the default one. So we just create it with default, and we have a pointer. We can do something with it, like with objects, like with structs. We need to use the arrow operator instead of the dot operator if the thing is a pointer, just that now we have also functions which we can call. And funny enough, if you want to call a function, if you want to put a function onto a struct, you can add a member to your struct, which would be just a function pointer, and then the calling syntax would pretty much be the same: arrow and then name of the variable holding the pointer to the function and brackets. So you can really emulate the behavior of C++, at least of the simple parts of C++ in C to quite a good extent. Now, of course, since we have defined this on a heap, when we put the breakpoint, let's say one here, and one here, what we expect now, naively, of course, would be that we have one call here, and two calls there. But this is not what will happen. We will see, of course, we have here a first call from there. We don't need this. Can put a breakpoint here. And then we have a second call from the other place. Then we have one destructor, and then we arrived here and we were done. So the thing is, since this is a simple pointer, it is like an integer, it just holds a value, and when it goes out of scope, it doesn't do anything. So this is not good. Since the thing still resides in memory, if you would do such a thing in your application, maybe not in the main function, but in some function which is called periodically, at some point your system memory would be very low. So of course you don't want this, and thus we need to free the memory. And like with C, but instead of using the free function, we use the delete keyword. And the delete keyword, like the new operator, can be also overwritten with our own implementation if we would want to. Technically, they are both operators, just have this set. And what delete does is it will invoke the destructor, and then it will free the memory for the class itself. So let's try this. So we have, of course, here one construction, and then we have the destruction from our delete. When we look on the call stack, we see where we came from. Here, not here, here. Wait, did this optimize this? Ah, no, sorry, there it is. There we have the arrow. So from here, the call goes to our destructor here, and when we just now single step the thing, then we of course arrive at our call to free. There we want to step over it. Then let's continue with single steps. And then here we are in fact in the implementation. Do we have source code for that? In the implementation of the delete operator as used by the current framework. But it seems we don't have the code for that on the system available. So we won't be able to inspect in detail how they implement it, but somewhere in the depths of the C runtime you actually have the source code for those simple functions. So if you are interested in that, I could look that up, but for now it's just important to know. Basically, if we would look on the C version here, that we had here the call to our destructor, and here we will have a some other call to another delete implementation, for which we actually have source code, which then calls another version of delete. It's a little bit convoluted, but here now we see that we actually use the free debug, which is like a debug version of free. But if it would be on a release build, we see that we would actually here use the very normal free from the normal C runtime, as we already have been using in our C examples when we had the lecture about memory management. So this is how this works. And the important thing here is that we have this behavior that as local object automatically gets the resources freed. So what we can, for example, create would be a smart pointer that would wrap a normal pointer, and then when it goes out of scope, call the delete function on our pointer. And of course this can be then complicated with reference counting, so that you can make copies, and only once the last copy is no longer referenced, then the memory is freed and stuff like that. But this is something for later. Today we'll just focus on the very basics of C++. So we already had here a few things, so let's proceed to the next very powerful feature. So we can, when creating functions, we can define them as virtual. So let's call it my virtual function, and let's make it just print that we called it. So printf. I need to add here \n, otherwise everything will be just one line. That's kind of tedious to read. And as said, we will print the function name and the class name. Okay, and at this point, of course, it's just quite a boring thing, because we just can call it and that's it. So at this level it's kind of not interesting. It let's remove the unneeded breakpoints. We just wrote that we called it, so as it should be. But where it becomes interesting is when we start and create another object which is related to our previous object. So we can create a new class. Let's call it class C my subclass, and then we specify from which other class it inherits properties. So, and we also have to specify how these other classes would be accessible when having an object of type of my subclass. So we say it's public, so we want full access to the parent class, and the thing can have multiple parent class, so you can specify a second one if you would have, and so on and so on. But for simplicity now we will just have one parent class. And what we also should do is we should define the destructor as virtual as well. Why this is important we will see a bit later. Okay, so we have here our class. Let's add to it a public constructor. Snack. Okay, and then let's create another function, the same name. And we don't need to say that it is virtual if the parent already has it as virtual. This is inherited. But what we can say is we can say override, which technically this is meaningless. It will not affect how the program behaves, but what it will do is, if this wouldn't exist, it will create a compiler error. So override has no function except that it helps us to ensure that the other function actually has been defined on the parent. And it's quite useful if you have more complex projects, because it makes it easier for you to maintain a correctness of your code. So of course we need here the semicolon. Okay, and let's now copy this, and now instead we will create, of course, everything. And also, just for comparison, let's also create a non-virtual function, which so that you can see directly how it differs in behavior. Let's just call it my function. Okay, and we will also create a second function with the same name, just without override, obviously. Here, and we just update the subclass. Okay, so we have our pointer. We created a subclass. We call both functions. And at this point it will be a bit boring, but this is okay. You can comment out those prints, since we don't need them right now. And oops, as you see here, wait, what, we called it twice. Because I call it here. So here, let's remove it from here. We just keep it here. Right. So in this case, you see that it called both functions on our subclass class. So it kind of is as one would assume that it would behave. But what we can do, since the class is derived, let's change the name here. Since the class is as such derived, you can assign a pointer to any type which is a parent type. So for example, here we assign the child type to the parent type, and the compiler says this is fine, which it is. And then we can call the same two functions on our child type pointer. Put a breakpoint here, we run it, and what we see now is that when we were on the pointer of our subclass type, it called both functions on our subclassed object. But when we switched to a pointer of type of our parent class, the non-virtual function there, it used the implementation from the parent, because for this function it just, since it's not virtual, it just goes by which type the object has been instantiated. It does not in any way check whether the object is what it should be, because even though here we have this thing basically just being the parent type, even the IntelliSense knows that the thing here actually is subclassed from the has been subclassed and might have additional members. We actually have not added here any members, so maybe quickly let's do that. Int my int2. Let's keep the same capitalization. Oops, my int2 also 0. Zack. I have a typo. Yeah, I have a typo. Zack. Okay, so as said, even though we have a pointer to the child type, the compiler knows and shows us the whole inheritance chain and all the members for our object. This can be retrieved, especially of course if you have all the debug informations. But plus there is also an additional internal mechanism in C which allows this type resolution. where was it? Now enable runtime type information. This we have not enabled here, but it could be enabled. Then we could during runtime also, not just using the debugger, resolve such things. But as you saw, it was not enabled, and still when we called the virtual function, the call ended up in the child type. So there must be information somewhere which are attached to our object and which allow when a function is called to call the right function and to, as we have seen here, to override the function. We can in fact compare the two function calls, how they differ. It was already running. Zack. So we see here the one functional call is quite simple. It just calls the function. It just hard-coded basically which function to call on compile time already. It just calls at an address and that's it. But when you go to the virtual function, sorry, I want to get out of this. The virtual function, the whole thing is slightly different. So we see here that RBP plus 87 hex is apparently the address of our object. So if we type this to our window, we should enable hex display, that is more useful. And if we check the addresses in both pointers, they will all should be the same, but this one is not. This one, these are the same, but the RBP, right, this is where the stuff is stored. So we need to actually unwrap that thing. Two asterisks. Yeah. So here we have our address, and as we see, RBP plus 78 hex is the address at which the address of our object is stored. So it's a position on the stack where the variable lives, and then here in the next, so it saves this to Rex, then it unwraps it, at which point, when put a breakpoint here, and run and print out Rax, we will get our address, which we wanted to have already. Not quite, wait. Didn't it work? That should have worked. Merge then. Yeah. So the thing then. They already read the value from this thing at this address. So this is again something else. But as said, we start with this address and then we read something from the beginning of our function. So okay, let's again go with Rex asterisk, and here we have a the first object which kind of exists inside our pointer here. So if we would take this thingy, merge 10, slash 10, then we get the same thing wrapped out of the object. And as we see what basically is implemented there, when we can look in the IntelliSense, is this underscore virtual function pointer variable, which we have seen already before. I just didn't mention it. And what this thing does is it's a function table. Basically, it's just an array of function pointers which contain addresses of functions which are to be used. And the first function will be the destructor. The second function is our my virtual function. So this virtual function table is created for every object if it has at least one virtual function. But whether you have one or many virtual functions, it doesn't make a difference. So the size of your object will always grow only by one pointer, because this table is then shared by all the objects. So everything that was instantiated ultimately as a CMY subclass will have its pointer variable pointing to a table which describes which functions to use for the my subclass. And if you would create a second subclass which does a different thing, then the other subclass would get another pointer table and would have its own functions. So while basically you need some extra memory if you make virtual functions, you only need realistically one pointer per object, and usually the amount of memory that you need statically, which doesn't grow with the amount of objects, is negligible, so you can disregard it. What of course is slightly more complex is that here you have two more operations before your function call can be executed. So it is not completely free, but also again here such two function calls are on a modern system in principle negligible, so I don't think you will find yourself in a situation where using virtual functions over normal functions would be a performance detriment. So generally this is not something that you need to care for nowadays. In the past it was slightly different. There with very old, very slow systems, any operation counted, so even such optimizations like not making things virtual which don't have to be virtual was already worthwhile. Nowadays it's from a code maintainability standpoint much more reasonable to just make everything virtual that you might expect in future need to be virtual, and not then have to come back and edit your code later on. Especially if you distribute something as a library, you would want to make it as flexible as possible. So unless you have a good reason to not make a function overwritable, like on purpose, then you can just make it virtual. And of course this also only makes sense if you expect your object to be subclassed. If you make an object of which you know it will not reasonably be subclassed by anyone, then there of course is no point in making things virtual. So it's always a reasonable trade-off, let's say. Okay, so was this until here all clear, or are there any questions? Okay, so no questions, so let's continue. Okay. So a few things which might be interesting also with regard to the creation of objects. So we have of course used the new operator, but there is another way how you could in a more manual way, without overwriting the operator for the whole project, create at least some of the objects from a different memory pool. So let's do this quickly. So let's define our class, semi-class. Oops, capital M. And usually I said you would use new, but what you can do is you can provide to new a memory, already allocated memory, which it should use to create your class. So we can use malloc. In this case it's kind of boring because it's again uses malloc, which the thing would use anyways either way, but it gives you the ability to use some other memory allocator. So here instead of malloc you could use my memory allocator or something, and then of course, so basically you have new and you insert these additional brackets here with which contain the address of a pointer, which will be used then for your object. And this will construct your object just using the already provided memory. It will not allocate any new memory for this object. Of course, inside your object, other allocations are not affected. They will do whatever they would do. So if you would have some very particular use case, you might, for example, like in a Windows kernel driver where you don't have the C++ runtime available, there you would create your object such that, for example, as a first argument, you would always pass some own memory allocator mechanism, which then could be used also here and in other places. But usually when creating desktop applications, using the default application heap is a very reasonable decision. It is reasonably performant. There are of course special cases where it's not fast enough, but in the general use case it is good enough and it's reliable, so no need to create something on. And then of course you can still use the thing the same way as you would always use it. Let's call getInt or something, or setInt. And once you're done with it, you want to destroy it. But of course using delete would not be good, because delete would then use the default free, which you might not want. So what you can do is you can actually call the destructor like a function, because it just is a function. It will just do all the cleanup, destroy all the memory which this object might have allocated internally, and it will just leave the outer memory not freed. So then of course you will at some point need to call free on the thing. And of course what you should never do is to call free on a class instead of delete, which has not been destructed, because if you just free it like this, then it just frees the memory. It doesn't call the destructor, and this means whichever resources the class internally has allocated will remain allocated, and that would not be good. So you always want to ensure that if you do manually such things, that you do that correctly. Okay. Good. Good. One other thing which should also be kept in memory. It's not correct English. One other thing you should think about when creating classes is, as I mentioned earlier, you have to define this as virtual, which usually if you expect to derive something, you should always do. Because let's manufacture the wrong case. Actually, this is okay. So to manufacture a fail case, let's add here a pointer. I don't know, int or char my string. Which here we want to new. Since we know new, we can already use new, and you can use also new for built-in types, like for char. Built-in types don't have a constructor or destructor, but you still can use a new, either one just for a single one, or for an array of them. Let's say, I don't know, 100, and then copy. Okay, let's be even more fancier. sprintf. No, sprintf. No, sorry, sprintf is correct. Sprintf underscore s. Now it's correct. Because we want to save version, comma. Wait, what does it want? Was it in bytes or in words? It doesn't matter. It's characters. For characters, it's the same. And again, you don't want to. Let's use just for completeness. That is not defined. That's in Windows H defined. So let's stay with. I think there is a model on num. Okay, washed. A lot of things in C++ are not part of the compiler itself, but just implemented in some header somewhere in some way. Let's say it like this. So if you don't include the right headers, you might not be able to use many things which, at least in the documentation, will be written as parts of the C standard. Because while they are parts of the standard, they are still implemented kind of externally to the language. Okay, so size of comma %d, and we just want to store let's say my int as a string with its numerical representation. And the way the constructor works is, of course, it first calls the internal constructor, which then calls, and only then it calls the next constructor of the child object. So once we are in the child's constructor, we can already expect everything that is part of the parent to already have been initialized. And of course here we want to delete. If you have an array, we should use the square bracket operator, although in practice usually it doesn't make a difference, but according to the document, the specification, if you allocate a single object, like just a char, then you just delete. And if you allocate an array, you use these brackets to free it. Okay, and this in principle, we don't need to do anything to it. It is already virtual. Right, so first things first, let's step here through the constructor, then we will step through the destructor, and at this point it will still work correctly. Right, so since now we can want to have simple code, let's disable on the runtime checks. That will simplify our code significantly, at least somewhat. Zack. Okay, so first we have our new operator, which we actually can take a look inside. Basically, we have here an object which will just use malloc to create this for us, and then it will, if it fails, it will throw an exception, but it works, so it just returns the block. Zack, and then here we arrive in the constructor of the parent object. First we have the child object, there we have the call to the parent object. So we start with this code here, but this code then of course calls the parent, and if we would have more than one parent, then it would call all of them one after the other, and only once it would be done with it, then it will go to our own code and implement whatever we have written. So that's how this works. Let's continue from here. Now we have the delete, so we go into delete, and this kind of operates in the reverse order, so it prepared a few things and then it jumps to our delete implementation, and it starts with the delete of the child, so the child will free and all its own resources, and once it's done, at some point it will call you skipped something. Wait, this was created virtual. Let's step again through it. We have stepped over an important step. Okay, so again, play here. Okay, single steps this time. Okay, so we have call. Then we call the destructor here for the child. We call here that was the delete for our my string. There we can step it out, and we continue stepping. Yeah, and now we call the destructor for the parent, which then does again its own thing. We step over it. Okay, now we go back to single step so that we don't miss anything interesting. And then when we are done with this and we turn here, we will then call the actual destructor, which will then free the memory. So as you see this way, even though the pointer on which we did delete was the pointer for the child type, for the parent type, it still properly deleted everything that the child also has allocated. And now if we would not make this virtual, we would run into a problem, because now if we call delete on a pointer of the parent type, not of the child type, when we step through it, we will arrive in the destructor for the parent directly. So at this point we have forgotten to free the memory that the child has allocated, which is not good, because it means this memory will stay allocated until the whole application at some point gets terminated. So we would of course not want this, and this is why whenever you expect a class to be reasonably derived, it is highly recommended to make your destructor always virtual, because then you don't need to care which type you deallocate. If this line would have been like this, then it wouldn't matter. Then it would call the destructor of the child, which would then call the destructor of the parent, and everything would be fine. But it doesn't, so to be always on the safe side and be able to handle and play with the pointers in a more flexible way, it is recommended to just make it virtual. And another thing that one might want to do is, if you are, let's say, let's create let's just go with this function. Now we have our virtual function, and you might want to be able to call something on the parent function. So for example, let's this one, make it virtual. The get is probably fine as is. Okay, so we are here, and if you want to be particularly annoying, we could make this private, not protected. And then, as you see here, my int is actually not accessible even in the child. So private is like really private. So here we need to call get to get it so that we can print it. But we cannot even set it. So here, even although we have the derived function, override, we need a way to call the parent's function and the parent set my int. And of course we could have like another one with another name, but that's not great. So what you can do is, if you prefix a function call with the class to which the function belongs, then you can call the function on the parent. Oops. So now if we have now example, okay, so we have here our thingy, and at some point, let's say here we want to set int 1, 2, 3. This set int will arrive in the child, which will then call set int in the parent, and then it will be able to do its own thing. As in this case, to keep things consistent, we want to also have the string representation containing the same value. So this way, now you just do the same set int, and it actually doesn't matter. Yeah, we do it on the parent type pointer, but it still will correctly also update our string representation. This is of course a very simple example, but it is quite useful. Also, if you would have a function which is defined outside of any scope, let's say here we have a int set my int for whatever reason. If you would have such a function, it would of course not be related to any object, but you could also call it just by using like the empty namespace as a prefix, and this then allows you to so for example, if you would have a function called write file, there is a function in the Windows API called write file. It is a very generic name, so if you have some own file object, you might also want to use a function with this name, and you could do it without any issues, and then you could call internally the Windows write file using the double point prefix. So that's how you can do such things. Yeah. Okay, so we have this. You can of course have as close to as many virtual functions as you want. Of course, at some point the compiler might run into some sort of limitation. So in excess of 1,000 members, not all compilers will want to work correctly. That is something I ran into myself at some point. Even I just had an object which had more than a few thousand members, and then the compiler just said it cannot handle it. The solution there is to just somehow split it into two objects, and one can be a child, not a child, one can be a member of another object. But before we do this, there is another thing which is quite interesting, which is that you can create a function on a parent which does not even exist. So let's do this. Void. You do it like this. You just write the prototype, then write equals 0, and this will have a significant impact on how the things behave, because if we now try to compile it, it will fail. As you see here, we had errors, and we had quite a few of them, because nothing of any of those types now can be instantiated. So if we want, for example, to avoid too many errors, I mean, we could, for example, put this on our subclass, then we'll just have one error. which is just slightly better. We had complained about 3 errors, but I think it should be only one, because we only create one object of this type. Yeah. And the idea here is that you can create generally an abstract interface. So let's actually do this separately. Class my interface. And what we of course will need for this, it needs to be a public interface. It will need to have a virtual destructor, which is fine when it does not do anything. And then let's just define a functions void my func1 and 2, 3, 4. So we define a few virtual functions which don't have a body. We of course just need to increment the name so that we don't have a name conflict. And this pretty much, so this object as such would have a size of 1 pointer, and it would just contain a jump table to all these functions, the destructor and then all these member functions. And then you would want to somehow implement it, so we just derive the class. My implementation. Public. See my interface. And so another fix, of course, for if we would do it here would be just to derive it and then implement the one function which is missing. And you, of course, can mix such abstract functions with into normal classes, but there is a particular use case for this sort of abstract interfaces, which is quite useful. So you will just play with that, and then of course here you need to implement all those functions so that they can be accessed. Oops. We don't need anything in the constructor, and of course the functions here now of course need to have a body. Even if they don't do anything, they just need to be there. And as soon as we have everything, then we can now instantiate it properly. So, and for example, we can create a pointer of type my interface. My interface is equals new c my. So we cannot create a new my interface of c my, because as we have seen before, this throws compiler errors because things are not defined. But what we can do is we can implement, create the implementation. This works just fine. And then we can of course call all those functions at will, my func1 through 4, whenever we want, 2, 3, 4, and then we can of course delete it. And the nice thing about such interfaces is that they really don't contain any code whatsoever. They are just a collection of function pointers. So often when you create libraries, it is recommended that you use such abstract interfaces as your interface, because what you, for example, would want to avoid is to have headers from your DLLs which contain some actual functional code to be included in a project, because then if you change anything to your DLL later on, it might cause an inconsistency and things will start crashing when the user would use a newer version. If you create such a abstract interface, however, and unless you change this interface, and since you created it for the purpose of not changing it, that would of course be not recommended, then this allows you to change your library as much as you want, and as long as you don't change this interface, the users will not be affected in any negative way. And the Windows COM interface, for example, uses such mechanisms a lot, so that you just have this call tables and then you can call functions on them, and you don't care for how those are implemented internally. Okay, so any questions so far? Okay, no questions. Good. So let's see. On the basics, that was that was it. So now you can in principle create your own classes and objects. So what we can do is we could schedule some homework so that you can train your newly gained powers and abilities. As you might remember, in the one of the last lectures, we have created this list in C. So we had this simple approach. We have some structs, we have some functions that do things on those structs, and of course here when we are using it, we need then to call in functions and always pass mylist to it. It would of course be now much more convenient to have the list to actually be a class, and all the functions which are here standing just on their own be just members. And functionally, as we have seen, this would be quite identical, since just this member goes away and then you don't need list, you can just access your things directly. So let's create a new project for that. Create new project. Next. My list, or just C++ list. Let's call it just C++ list. The other one was simple, so this will be C++ list. We create it. Okay. And the idea here will be to create an own version of basically port our simple list to C++ with all its features. So I think you had some assignments to make it doubly linked and so on and so on. So with all those features, we would want to port it here. This we will rename to just main, because CPP list will be then needed to contain, depending on the details of the implementation, to contain the your function. So we can create a class using the class wizard. Basically, it's quite trivial. Just sim my list. Let's just call it my list, or let's stick with CPP list. We don't want the C prefix in the file names, so we remove that. And you could even specify a base class, but in this case we don't have one. And what the whole thing does, it just creates us a almost empty file and another also almost empty file. So the wizard doesn't do much, but it is still nice to have. And of course want public, so homework from the, what's the 08/05/2025. Oops, suck. Yeah. Okay, so out the to C++. Okay. Add all needed functions. So what we need append, prepend, remove. What else did we have? We have insert, append, remove, find, of course. So append is append, and prepend we will call insert. Insert, append, remove, find. We can add a reverse find if you want to search from the other end of the list. Yeah, and protected here there will be a struct as list entry, which will contain our can we do it protected? Let's see, because this complicates a few things, since we have not specified a type. You always derive from it. So before we can do this homework, I will need to show you one more mechanism, which is quite useful. Then we could make this object even much better. So what we could of course simply do is to have this struct here publicly defined, and then just normally work the same way as we did here, that we create an object which has this as a first element, but we can do it in a much more elegant way. So let's take a look on another mechanism that C++ contains, and then we will go back to our homework and improve on that. So we'll create another project for the next important thing, which is so-called templates, which I, by the way, already mentioned today. Great. Okay, so templates. Templates is a mechanism that allows you to write, well, a template, either a function or a class, which then can be, from which then the compiler can create individual implementations. So let's start with something very simple. Let's say template, oops, type name t1, and that's already all we need, or just t, we don't need too much. So this function will return something of type t, and t is the placeholder for an arbitrary type. My function 1, and it will take two variables of type t, var1 and var2 t, and what it will do is it will just return t1, var1 plus, let's capitalize this, var1 plus var2, and that's it. So it's really as trivial as it gets. Let's just implement something. Let's hash include std, and now let's define some variables. So my int1 is like 1, my int2 is like 2, and let's say with also double, my double 1 is like 1.11, and my double 2 is 2.22, and then let's just call the function int my int3 is equals my function, and you can use the same function for integers as for doubles. Double, oops, double 3, and then of course everything will be a double. Double 1, double 2. And if this function would take ints, then if we feed it with doubles, it would truncate it, and the result with doubles would be just 3, not 3.33. But when we put the breakpoint here, we forgot the breakpoint. Let's run it again. Then we actually see that, well, the int is as it should be, and the double, double, oops, double should be double. But the double also now is correctly 3.33 and some rounding error. So, and if we step in those functions, we'll see that the one function here has this address, and the other one has a different address. And in fact, these are different functions. So when we step into them, you have an implementation for which just uses normal operations, add and so on, for integers. And when we go to the next one and step into that, once we are past the boring code, we see that it uses an implementation and the opcodes for doubles. So effectively, and we have some garbage here because we have not disabled this just my code and other things. So basically what happens here is the compiler takes the type, takes the function, copies it, adds the right type instead of t, and compiles it. So it creates really completely new instances in machine code of our one function. And we can in principle create as many such functions as we want, just by passing them different types. Of course, if we would now mix types, if both are defined as the same type, then the compiler would probably decide based on the first type and then cast the other type. So if we would take this, let's see what it will do, double 4, and we feed it an int and a double. Actually, it doesn't even want to do that, because it says that it doesn't have a function with the right arguments. So the compiler here even just outright declines the operation. We could of course specify the type, force a certain type. Let's say we want to force int, and then it's fine, because so you specify here basically a list of types with a comma separation. In this case we only have one, but we could have more. And then you can here have different types, as many as you have defined at top, and then you tell the compiler which type to use. So for example, if here I would force it to use int, then it would use the int implementation, and the result of double would of course be just 3 instead of 3.33, because it just used the int and had casts everywhere. So this of course would not be something that we want, and of course in the below case we could then force a type, and then it would work as well. And if it's confused, then it says it cannot do it. So what we of course can do is we can create another function which then have two types, t1 and t2. So let's say return is the first type, and t2, we could of course have then also t2, oops, typo, t2 as the return type, so we could do whatever we want. Let's quickly return this, so we have this line back here, and it needs another name, so let's call it type 2. And then it will of course work, and but of course the return will be then int, so this will be an int 4. And this can of course be arbitrarily complex. So for example, we could create some structures. My struct A with int var a and b and c, and another struct b, semicolon, struct b with various let's say with floats. Okay, and then we again create a function that does something. Let's call this function, function, but we could even, yeah, let's go with function 3. We have two different types, and then let's say it would be defined such that this will always take var b. So then if we take of course function 3, the first one, let's say it's fine to be an integer, but this thing of course will not work, because a double doesn't have var. So if we try to compile this, it will throw an error, and the problem is here that at this point the IntelliSense is already not smart enough to figure this out, so it doesn't show us an error anywhere. And in fact, once you start to work with templates a bit more, you will notice that various template related errors only are thrown during compile time, and the IntelliSense is not intelligent enough to be able to find them. So here, for this to work, of course you would need to use one of our structs, doesn't matter which one. My struct b, we will initialize it to something. So b has floats, so 1.11, 2.22, 3.33, and we should add the f suffix to indicate that it's a float and not a double. And now if we and the semicolon, and of course need to pass it as argument and run it. Oops, yeah, this one we already used this name. So use another one, and now again it compiles. And as said, really it's kind of just a game of search and replace. So it just creates another function and another function and so on. There are of course scenarios where you might want to have a function with the same name, and then still being able in some way to handle a type which is completely different. So for example, let's go with our function 2. because we at least need to the ability to distinguish those types. So we will create a string char maestra is equals 1, 2, 3. And what we would want now is we would want to use our function number 2 to be integer 6. That comes out here to add a string representation of a number to just a number. That might actually not even complain, although it does. But if it would, then it would just do nonsense. But here it more or less tells us that it cannot do the plus operation on a character string. So what we can do is we can create a specialization of this function. Char_stern. And then we just write something different that will make sense, like Atoi, which takes Atoi is a function provided in the standard library, which takes a character string, and creates and basically passes it and gives you the numerical representation as an integer. So if we run it, it works more or less. Yeah, 1 plus 1, 2, 3 is 1, 2, 4. And you could of course create such specializations for many other types. So if you would have a white char or something else, even one of our structs, you could create such specializations, and whenever there is no specialization available, it would default back to your template function, which is quite a useful mechanism. Okay, any questions so far? Okay, if there are no questions, so let's continue. Likewise with functions, you can use this template mechanism to create other things. So for example, we could create our struct as a template. Let's call it struct x with type t, and then we just replace type t, sorry, the float with our type, and then we have a struct of an arbitrary type. So for example, here we could use our struct x. We would need to specify the type float, and then we could just initialize it the same way. And here, of course, our template function will just consume it just fine, since the names are correct, and it does what it should be. Also, at this point, of course, we could change all the other names. We only need this var b to be there. And the same thing we can create with our with a class. But one more thing before we do that, you can use the type def keyword to create something that will really behave like a simple type. Let's say this time double, and we'll call it my struct c. And then of course you could use this instead of the more complex implementation. Oops. And here, just since we are using different ones, just remove the letter so that we are not under the impression that it would actually be of type b. And then of course we use without the f, since we have a double and not a float. Although this would not be a major issue, just cast it and it will be fine. And with this it then of course also works nicely. Okay, so this much to this. And as said, what you can do is you can create a whole class just like the struct here, which would then contain some type on which you then could do something whatever you want. So for example, we can create a class just for testing, so that we demonstrate this. We have just to think about something that what the class would do. Class, let's call it my print, and the job of the class, the job of the class would be to just print something of type t. printf. We need to specify some type, of course. So let's say, to make this a bit more interesting, well, or we just stick with t. So just print whatever we get as an integer. This is not correct, not really the best thing we can do, but it would work. So you can then, although this is a boring example, let's maybe do something else, something more interesting. Let's create an array. My yeah, this is much more fun. Let's create a my array class. Okay, this will take a count. It will have a protected member, t asterisk m data. Then it will new count t. So it creates an array with count amount of entries of type t with no constructor, and then it gets a destructor which then just deletes that. Delete. And we want to somehow access it, but that's for later. The simplest, of course, way would be have a void get add get add size t. Actually, we should always use size t for count type thingies. And what we also should do is we should save our size. So we should actually call it count. We should save this so that we can then check whether we are trying to make an out of bounds access. As you might remember, before t const t returns value, and this get first we want to set. As you might remember earlier, when we used C++ arrays, we ran into the problem that you could specify an invalid index. For example, if you had your loop array, sorry, your loop counter go too far, and then you exceeded the bounds of the array, and then you overwrote some memory. Here, if you create such a smart array, we can first check if index is more or equals count, and then just return. It ideally would want to throw an error for an exception. Which actually what we could do is we could have here a return value, and we just return false. We don't even need to throw an exception. It just tells us whether that was successful or not. And of course the other function would be t get add index, and it's very similar. So it also will validate. So reading invalid memory is not as dangerous, but of course also something that needs to be avoided. So we can use t like this. To what it creates us basically is an empty object of the type which we specified, and if everything is fine, it returns a copy. And this can be const, and this returns a copy here to our entry, and this thing here then does its thing. So this is like super convenient, because now if we have a scope somewhere and we create something, let's say of type int, my array with let's say 10 entries, then we can initialize it in for int like null is less than 10. We should be smart. But we need to get count, which we don't have implemented. Let's add this quickly. Size t get count. That should be a one-liner. Count. So to get count slash e++. This way we already know that we will not access anything we shouldn't, and even if we would, then it still would not corrupt memory. It would just return false. So e and value would be, let's say, we just feed it a random number from our not so random number generator, and then of course we can do the same thing to printf %d Abstand, Komma, Punkt get at I, yeah, and the, oops, wrong bracket, and then we just printf a new line. Yeah, nice. So, and once we exit the scope, it will destroy our object for us. So we can put breakpoints. Well, let's just put them here and here because those will be called many times. So we don't want too many breakpoints. Oh, we have a bug. New type. Right. Wrong syntax. Okay. So the constructor does its thing. The thing printed the values, and then the destructor is automatically called when the object goes out of scope. So this way we could already avoid having to running into a memory leak. Our array wrapped our raw C object, our raw C array pointer, and provided us a safe interface with which we could do whatever we want. And now the great thing about it is that we can that it is not limited to one type. We can do the same thing with a double. Just that here it needs to be a %f. No, f. Or let's go with a float. Float. It doesn't matter. Let's stick to double. With %f, and maybe for rand we will go with 100.0 times rand. That is boring. Let's do it differently. Rand divided by 1000. It will give us a nice number with some commas. Let's see. Of course, we don't need those breakpoints anymore. Yeah, we get nice here things with comma values. So as you see now, our object can really handle whatever we wanted. And here we use this placeholders. And for example, we could also create here a structure which would then use T as a placeholder, and so on and so on. So this brings us back to our homework assignment. So we have our list entry, and what would be great here for making it as flexible as possible is that we would hold the data so that this whole thing will be a template. Type name T. So we have our thing. It will of course have a pointer to the previous previous and to the next, and then we'll have a T data. Okay, and of course this then of course can be put into a private protected section, since we don't need it externally to be able to access the thing. And what we also of course need is a mp head and tail. And what also would be very nice to have is a size t mu count, so that we keep track how many elements we have. Since this is not an array of any sorts, we have, if we would want to find out the element count, we would actually need to go through the whole thing, unless we always update our counter variable. This makes it much more convenient to use. So here we also had such a counter variable which we kept up to date, which is quite nice. Okay. And I think this should not be too difficult, because mostly it's just porting the things we made in SimpleList, just with some additional understanding of how those things here are to be used. Okay, and we have one limitation which we are lacking, is we need a function to enumerate or to iterate through everything. So let's call it iterate. And this function, let's implement one here just as a demo. because it's a very trivial function, just that because here we could like access the internal stuff and we didn't need to have a function that does this. But here, since the thing is internally abstracted, my iter function, I think it's written with 2t. Iterate list my iter function, and then the thing will just call the function on every with the parameter on every but just each time, and that's it. We could, and it doesn't return anything. Although we could make it actually return ball, so we might want to be able to abort. So if this is false, then we return false, and else just return true. And such a function, just without of course the first argument, because that's one is implicit, will be needed to exist on our C++ list. So here I will just, or in CPP, add this so that I don't need to upload the okay, the comment is not commenting. Right, yo. So, oops. Let's quickly check with Google whether you write iterate with double T or not. No, you don't. Use 1T. Then let's quickly fix that. So here. And here. Right. Okay, so 1T. So this function will be very important to step through all those things. And when we later look on some standard container types which do similar things, provided as a part of the standard template library, we will see a mechanism which is quite convenient if you want to step through lists and stuff like that, which is called iterators. And once we learned how this works, there will be a part 2 for this homework to create such an iterator implementation for our list here as well. But for now, of course, we don't want to complicate things too much. So we will really just make this a simple porting task. And you should not be scared of this being a template. Oh, and since it's a template, we don't need the CPP file. If you create template classes or template objects in general, you create all of them only in the header, because the compiler, wherever you might want to use it, needs to see the whole implementation. If you would hide something away in a C PP file, then the compiler would not have access to it at the point and could not create the right function implementation. Yeah, so that's how this behaves, and it should be quite simple. As said, the fact that this is a template only means that you can use here this T. The rest of how you write the code remains perfectly identical to a normal non-template class, except I said that you keep everything in the header. Good. Here we have a sample function so that you know what to do with that. And now let's quickly return to our templates, because we were not done with them, not yet anyway. So what you can do with templates also is you can create a sort of template which can take multiple arguments in a certain way. So let's create here a very convoluted example. So void, let's call it my print. My print. Let's make it work just with int. So int var1 which we just printf, zack, %d, comma, sorry, var1, and let's edit a \n. Then we will create a, let's say, template for floats or doubles, because floats and doubles use the same register, so we always use just f. This will be of type t. And then let's do the same thing here, another specialized version for characters. My print const char stern, so just %s to print that. Okay, so we have all the types, and then let's first see what we can do with that. So we can just call my print, of course, normally with each of those types. So we can use floats or anything that %f would be valid for. Unfortunately, we cannot make this much more easy. We could of course make it such that we can change the letter by providing another argument there. That would of course be also one way of doing things. But I think for a string this already is kind of good enough. So what we do here is type name t, type name t, typos everywhere, and we could create a template which takes a variable list of arguments two. No, this was differently. Type name types. That's how we do it. Type name types. Then void my print again t var1, comma types1. Oops. Types lowercase var2. My print var1 we can print normally, and then we will also add a my print var2 and 3. That should work, I think, and then let's use it. My print 1, 2, 3.45 comma blah blah comma oops. Okay, and let's see what this does. Zack. Typo. Okay. So we have the other lines that we printed. We can make this smaller. And what it did here is basically, when we go to our function here, so this one was more or less implemented normally, and here it kind of called the same line multiple times for the different types we have entered. So it worked for an integer, it worked for a double, it worked for the strings, and each time it used one of the different functions provided here at the top. So this is quite a complex way of using templates, but there are situations where this actually might be quite useful. If you want to, have some sort of variable argument function with templates, then you can do it like this. We can also step through it so that we first we disable the useless junk, so that we have a nice clean code generation. this and linker. Okay. So again we have our breakpoint, and then when we step into this function, okay, miniaturize it too much. So let's first, of course, we need to prepare the arguments, which we have here. So this is just done. And once we step into the function, we see an implementation that implements. So here we have our print with e, and then we have our next implementation here, which kind of calls itself recursively. So this is how this works. It does not like replicate this line however many times you have, but it kind of tells you that there can be many arguments, as many as you have specified, and effectively what it does is it kind of unwraps the first argument. So then we do the first thing here, and then we call it ourselves with the remaining arguments, so argument -1, and this thing is repeated as many times as long this is something. And at some point when we keep, so here we have the print which is specialized, so we can go it out of it, we get here, and then the whole thing repeats as we step over it, and at some point, okay, then I think we already reached the end. No, we didn't. And at some point we will have reached the end, where it will no longer have a further function. This was now the end. So now when we stop over this, we'll be just stepping out of everything. Or not. Now we actually now stepped into printf. That was a mistake. Now we step out of it. And we step out of everything. So we also see here, you saw here the call stack, how it looks. So this is kind of quite a useful thing in special scenarios. For others it's useless, but it's good to know that you can even create such very exotic things with your templates. Basically, that you can like call one template from another template, and even recursively. So for example, you might have a template which creates an object, and it takes an argument with a memory allocator, then, and it needs of course the type to create, and then in the same function you want to be able to pass the arguments which will then be passed to the constructor of this function. Actually, we could create such a test case here to demonstrate that. So template types t** make something, or let's call it my new, that's better, which takes types, params, or let's, yeah, we could also create a memory allocator. Let's do that. Windows H. So as you might remember, we had this function called create. Was it heap create? Heap create, which creates a heap by type handle. So argument 0, initial size 1 page, minimum size 0. My heap. Okay, and once we are done, we of course need to, what was it? Destroy heap, and that's was it destroy heap? Or was it heap destroy? Heap destroy. And internally we had like a heap alloc and heap free and stuff like that. So we have handle my heap. So actually we could pass this as an argument. It doesn't need to be a template, because we will be using this the known function. So we leave this specialized, and then we have an object we could use. Yeah, let's go with this struct C, which is a template on its own. So And one more thing, modern C++ has the auto keyword, which you can use as a stand-in for a type. If the type can be inferred from the rest of the equation, then it will work. If it cannot be inferred, then it will tell that it's ambiguous and you have to specify it. But let's do it like this. My struct C. Let's go like this. And that's of course a pointer, although it can infer that as well, so let's just stick with that. And then we need to specify a type, so my struct here. Actually, will that work? It actually might be a problem. And then we specify the handle. And but the struct doesn't have a constructor. Let's add a constructor to it. Where was it? Here. TA, comma B and C, B and C, and var A is equals A, B is B, and C is C. Okay, and it's 1, 2, 3. And that might just work. We didn't destroy the object. It's not happy. Oh yeah, sure, that should have been C. And this must return a value, sure. Return new heap alloc heap flux 0 bytes caesar of t. One more t, and here we can then feed the things which we have got params into the constructor. Okay, that should work, and it did. We created our structure initialized with 1, 2, 3, and of course we should delete it just for correctness. But it doesn't have actually destructors, so let's add one. Constant. I mean, this thing in this case doesn't need a destructor. Oops. But let's add one just in case the T thingy would be something more complex. So the type you use for your template can be arbitrarily complicated. So that could be a whole other type or something. Heap. Oops. Heap 3. My heap, comma flux 0, comma mem this thingy. Oops. That's the right one. Okay, right. So this is done correctly. Yeah. So as you see, there actually are quite useful use cases for such a mechanism with a variable amount of template arguments. And I just noticed I forgot to show you one more thing with regard to the C++ classes. That would be how to call another constructor. So if we called it here, of course, implicitly, but if we would want to call it explicitly, we can just write double point, the name of the parent class, and rand. So this syntax here will call this constructor instead of the default nameless constructor that would be called otherwise. So if we don't add this line, this one would be called for us automatically, as we have already seen. But if we add this here, we can specify which one we want, and then of course pass arguments along. And what we also can do, generally speaking, is if you want to initialize other things, you can also initialize them from here. Like instead of using the initialization here, you can initialize them like here. And this actually is needed in a certain scenario. So obviously the other way of initializing things is just from there, but if you would have a variable which is defined as a const, then even inside the constructor you can no longer write to it. At least the compiler will not allow you to do that. So what you do instead is you initialize it through this initialization list, because here you are in fact allowed to write to the const variable, because even though it might be const, it needs to receive a value somehow. It needs to be set. And since setting variables this way was introduced later, the initial way of doing it is this method. So that's that. And there is one another thing which I thought I might want to show you, a sort of let's call it a catch-22 scenario. So as we have seen, when we call virtual functions on anything, they work correctly by calling into the child's function. That is, unless the function is called from the destructor. So we can call it from here and then step into it. And when we do it, we notice wait, that shouldn't have been working. No, sorry, the other way around. From here it still works because we have not finished our destructor. If we would call the function in the parent, then that's where it fails. So let's add one more breakpoint. Right here. So we are somewhere here. My subclass. Okay, we use that thing somewhere else. My subclass. Okay, now we are where we wanted. So we start. The other calls were from different free operations. So for this delete and for this out of scope. That's the first time we go into the subclass element. So we are here. We finish our child thingy stuff. Let's say. And when we go here, we see that we are loading one address, which complicates things, because then when we arrive here at this function, even though let's step further, step, even though we are loading, we are here now calling, even though it would be a virtual function, we are just calling our own implementation. We are not longer calling the function of the child. So this is something which kind of makes sense, because the child has released all its resources, so one would assume that everything we might want to do in the context of the child would not be valid anyways. And if we have if we want to call any functions, we can only do it on the level of the parent. But there are situations where you might think that you could use this virtual mechanism to do something smart, and then it will fall apart. So the scenario where this fails is if maybe we should actually set up, we have a few minutes left, a full demo of such a case. So we have class, it's my opt1, which public has a constructor and a destructor, and then we derive something, my opt2, this should be virtual, from opt1, oops, okay, and let's say this thingy would have some sort of structure, and s1 int x, and then it has of course a pointer to it, so s1 asterisk m data, and we want to get rid of that, and we want to create, and the idea is that here in our child object we want to have some s2 which is derived from s1, s2, which is derived from s1. It has, let's say, a y variable to make things a bit more complicated, and this thing would have a non-virtual destructor for whatever reason. The correct way of doing things would of course be to create a virtual destructor on this, and then just delete the thing from here. But another way of doing things, for example, would be that you have some s1 asterisk, create data virtual, create data. So this one is a virtual interface. And then you would need to have also something to. Alright, this needs to be of course defined after we have defined our type. Maybe here. Then you would have another virtual function to destroy as data. Oops. Okay. And then since you have your S1 not having a virtual destructor, you know that you need to do it here. So the first thing, just creating objects which are more complex in the child is perfectly fine. But then trying to destroy them, P, and since it is S2, then you would need to cast it, is as said is problematic, because if you would have here in your destructor something to clean it up, if if data, then destroy data, then this will not work, because it will kind of try to call the non-existing function, because it would never try to call anything on the child from within the destructor. So the correct way of doing such a thing would be to just delete the thing. Oops. And give it because if we delete it without this being the destructor being virtual, then the delete will not clean up other memory. Here we don't have other memory, so it would be fine, but ideally you would want just virtual S2, and then you completely don't need this delete thingy. You still have your create, which will create more complex objects, but those objects will take care of their own cleanup through their own destructor being virtual. This of course makes this object larger by 1 pointer, since it's now a object with a virtual function table. But even though that might be a bit wasteful memory wise, it is the proper and clean way of doing it. Another workaround of course would be to clean up everything from the child's destructor such that the parent doesn't have anything to do. That would be another approach. But I just thought I will show you this, since it is a pitfall one might fall into when trying to do things from the destructor and thinking you might be able to do something with a virtual functions. And one more thing that is worth showing is that what you can also do is you can create a so-called static function. Void my print. And a static function on an object is pretty much like a normal function. It does not keep any reference to the object. So int x, let's call it, and int f %, we can print x just fine. But if we try to print a variable, it will complain because the variable does not exist globally. You can then of course define a variable as static, which then again means the static variable will be shared by all instances of this object. So my int, my but you cannot initialize you should not initialize it like this. As you see, it doesn't allow you to. So the static one you can now print %d and %d. But the thing needs to live somewhere, so you need to in some CPP file, define it like you would define a function with the class prefix, and there you can assign an initial value. And once the class gets instantiated, the object, the CPP file gets processed, this will be added to the initialization list of the application, and address for this variable will be generated, which is then shared by all the objects. So every instance of your CMY class will have access to the very same variable. They will share the data in it, which in various scenarios is actually quite useful. But you of course need to take care if you have a multi-threaded scenario that and multiple threads accessing the same object. If they are using the static variable, that then you need somehow to guard it with a synchronization object or something, but this is a subject for later. Anyhow, about this static function, so if you have something, you can of course call your static function like this, obviously, but you can also call a static function completely outside of having a pointer to anything. You just specify the name of the class on which the static function is defined, double point, the name of your function, and you can pass the arguments. And it will be able to operate. It will still have access to the static members of said class. And as any static function, it will have no access to anything on a given object. Therefore, you don't need an object. So as you see here, you can call it like this statically. And the last thing to show you where you might wonder where such static variables would be useful. For example, if you want within your entire application have only one instance of something and keep the code as simple as possible, you can create a so-called soliton, which is just a special way of using classes. So let's create one. CMY soliton. And the way you do it is, so of course you have some public functions. Let's say void myfunc that does something like printfing something, test, semicolon. Okay, so you have a function. This is public, and then you create a static function. Usually you would call it instance or something similar, which returns a value of your soliton. And to be able to return something, you would have, for example, a private variable instance, static one, of course. And the way this would work, instance would check if instance, then return instance, else instance is like new instance, and then it returns it. So actually we can simplify it. If it doesn't exist, make it and return it in either case. And then of course we need to give it a place to live, so we put it here, oops, ptr. And if you want to ensure that no one can create another instance, you can hide your constructor here. So you make your constructor private, and then if we are outside, we cannot auto test is equals newts my soliton. It complains because it's not accessible. So let's see. Inaccessible. So the correct way to use a soliton is you use instance and then you call your function on it. Zack. You could of course cache it and make like auto test is equals or something like that. Then you could of course use it like this. That also works. And this is in various situations quite useful. For example, you could create an object that stores configurations for your project, and then you would want to access the same settings from everywhere, and you might want to make it such that you don't need to always access some root object that contains all your other things. So then you could of course just use a global variable instead, but this is kind of a more elegant way because it also ensures that no one else can create another instance of the thing if you would if you care for that. There are more things about classes and how they can be used, but this is something for in the next lecture. Just to quickly give you a hint what you can do. In C++, since you have your objects, which can be quite complex, you can define custom operators. So you could create a class, and then on the class you could define what plus means. So for example, you could have a class, a string class, where if you use the plus operator, you can concatenate another string to it, for example. Or you could create an own integer class which has a wider value range than a normal integer. For example, a 128-bit integer is used in cryptography, or a 256-bit integer. Of course, internally it can only still operate on normal integers, but you would just implement own logic to make it behave like a number bigger than what the hardware can handle, and you could use then this number in C++ as basically like a normal number. You would of course define multiple operators such that you can add those numbers, plus you can add normal integers to those numbers, etc. So this is quite powerful, and during the next lecture we will take a look on such things. So we will create an own smart pointer maybe, and of course some own operators, and maybe a simple string class we will see, and also we'll take a look on C++ exceptions, which are quite useful. And in the next lecture we will take a look on the standard template library, which contains a huge amount of very useful container types like lists, maps, etc., and also of course strings. So this is something quite important. A nice thing about the standard template library is that it is platform independent, so you just need a sufficiently new C++ compiler and you can write your application and it will compile on Linux, Windows, Mac, and work just fine. In fact, the more modern versions of the standard template library are going above and beyond just providing simple templates which are, so to say, self-contained, but they also provide platform-specific implementations of commonly used things like synchronization objects, file access, even multi-threading you can do with modern STL versions. Whether you want to is a different story, because since it's kind of a minimal common denominator of what every platform should be able to do, you might find it a bit too restrictive and then prefer to use some own implementations. But generally speaking, it is very powerful, and since it is platform independent, it is recommended to use it. And since we are running out of time, I think this is a good point to stop. I will upload the template and the C++ basics projects, as well as the CVP list homework project to the Moodle, and the recording to YouTube, so that you can watch it again. And if you have any questions with regard to the homework, you can email me at any time. So we will see each other, I think, next week. I don't think there are any holidays anymore. Almost a month of break, I think, was long enough. So have a nice evening, and we will see each other next week. Bye bye.